It is my honor to invite Dr. Matthew Young here, our UNH research scientist, to present today. I had real trouble narrowing down the comments to be brief enough because we go way back to the undergrad days.
My talk's in 15 minutes.
Oh, okay,
so
great.
I knew
So
you had like half an hour.
Yeah, that's right. I'll do that, and then I'll just get your talk down. So think about it. So actually, even just as we were walking up the stairwell, getting flashbacks from Physics 407, 408 studio problems, and doing some work in Mark Lassard's office too. So speaking of Mark Lassard, Matt did quite a bit of research, even as an undergrad. A couple of papers coming out of his work with Mark's group there. So yeah, 2012, I think, is that when we graduated? Yeah, 2012 with a BS degree here at UNH. And let's see, and jumping ahead, so fast forwarding, 2018, PhD from Boston University in astronomy, working with Mears Oppenheim, I believe, the PhD, and focusing on numerical simulations of collisional plasma instabilities. I might hear some of those related themes in his talk today. Then postdoctoral work back at UNH, where we're glad that Matt has now become a research scientist on the team here, studying these types of topics. And today we're going to hear about SEP events in particular. And I'll just mention too, I think the most recent video I've seen of Matt, as a side note, in addition to his research work, as a very musical individual. And I saw a particular concert where he actually pauses mid-chorus and derives, I think it's a wave equation or a plasma physics instability criterion. So today, we might be lucky enough to have the reverse happen, where mid-slide, Matt might just break into song randomly. So no pressure, but we'll see. We're ready and waiting. So Matt, take it away.
Thanks, Jason, for the introduction. Unfortunately, everyone leaves out the part that I already had a BA in anthropology from UNH. You can see how much where that has gotten me. It got me right back at UNH studying physics. And yeah, Jason is right about that video. There was a great unplugged musical event every year at Boston University, and I think I had just taken my qualifying exams, my third or fourth year qualifying exams, and we were playing, this group and I were playing Weezer's Sweater Song, which, if you are familiar with it, has a spoken word component, and so I took the liberty at that time to derive the gradient drift, gradient drift instability criterion instead of usual artistic license. If I can find the video, I'll spam the big science and email with it. Yeah. Okay. Yeah. So I'm going to talk about SEP events and what we call, we being the I guess the Healy physics community, widespread SEP events, and I'm going to talk about what that term means and doesn't mean, and why I'm being sort of vague with it anyway as I get into it. So, if you have a preconceived notion of what a widespread SEP event is, then I look forward to discussing your definition as it relates to this research. But the other part of this title is the particular numerical simulation I'm using, and of course we'll go into some more detail, but I'll just tell you that this is a simulation that Nathan Schwadron created and really originated at Boston University, but came of age here at UNH, and it went through a little bit of a quiet period, but we're trying to revive it and breathe some more life back into it. And so this has been a really nice topic to explore with it. And this is work that I'm doing with Paul Portowal, who is also a researcher at UNH. And the way that this works is continue with the slides. Okay. So a little bit of terminology that some of which will come up a lot, some will not come up very much, but we may as well hit it. I'll talk a little bit, or I'll refer to galactic cosmic rays. These are high energy ions that are coming from outside of the solar system, not really a focus of this research, but related when you're worried about space radiation. Solar energetic particles are the key focus of this research, and SPE originally was a solar proton event. It's been sort of adapted to a solar particle event, by which we really mean an increased flux in solar energetic particles at a particular location. And then a ground level event happens when SEPs are energetic enough to to reach Earth's atmosphere and create secondaries that are then visible on the ground. So you may be quite familiar with that work. And then I have a little helical curlicue that would be impressive if it weren't for Jason's Desmos simulated things that he'll show you sometime. Supposed to give you the idea of a particle gyrating in the magnetic field, just so we make sure we're all starting from square one together. Okay, so historically, the community has split SEP events up into gradual and impulsive events. Gradual, prototypical or canonical gradual event being shown on the left, and canonical impulsive event being shown on the right. And the prevailing understanding was that gradual events were due to CME-driven shocks, particles accelerating in the corona and in planetary space due to these CME-driven shocks, and then impulsive events generated by flares. That picture, as the science progresses on, has become muddy and blurry, as it should, as we learn more about these events. And in particular, I'm not going to spend much time on this distinction because of my interest in exploring just the observations of widespread SEP events, whatever created them. But another aspect of SEP events are the effects of transport, and this is some old data from Beta and Helios showing how the peaks in the Helios data in the blue lines were smoothed out by the time they got to 1 AU. You can look at, well, I mean, so the top trace in each is electrons and the bottom is alpha particles, but the behavior is similar. And so that's the effects of that radial transport or field aligned transport has on solar energetic particles. So that's another thing that's important to understand. We're talking about the spread of particles through the heliosphere. Another important application, which we work on a lot in this when we're talking about SEPs, is radiation prediction and mitigation. And so the one point I'm going to make here about that is that so this is work from 2010 by Frank Kuchnada, who's done a lot on this. On the left panel, there's the galactic cosmic ray flux, dose, effective dose rate. And the point there is that it's basically the same for all of the amounts of shielding that they tried, and that's what's in the key there, 5, 10, 20 grams per cubic centimeter of shielding. But the SEP dose changed a lot with the amount of shielding, and so the takeaway from this slide that's important about understanding SEPs and prediction is that you're probably just getting GCRs, but if you can predict where SEPs are and alert your crew or your mission operations, then it can make a big difference if people are able to get behind enough shielding. But the aspect of SEP events that I'm going to focus on mostly today is their variation with, and here it says location, but what I really mean is longitude now. Back when we only had satellites at L1 or just ourselves observing in 1 AU, and then when we had some other observers at 1 AU, not necessarily at Earth, maybe location and longitude, well, before stereo, maybe location and longitude are the same thing. But now we have a fleet of satellites, PSP, Solar Orbiter, Stereo A is still giving us data, lots of, and other satellites of planets that are really allowing us to probe the heliosphere variation with radius and longitude. But this picture is part of the motivator for the research that I'm talking about, because the observed SEP flux, or protons specifically, varies, and these are varies with location, longitudinal location, specifically location with respect to the shot frame that the CME is driving on. And for example, you can see that for an observer here, I'm sorry for, I should use my mouse. An observer for which the CME comes off the west limb, the SEP flux peaks pretty quickly, whereas an observer that sees the CME come off the east limb sees a more gradual increase before the softer peak right here. This is the sort of canonical picture for for widespread events and what I'm going to get into. So with that in mind, let me describe the model. EPREM is, in this context, the energetic particle radiation environment model. Now, the real historians out there will know that it began as the energetic particle radiation environment module as a component of first EMREM, Earth and Mars radiation environment model, and then PREDICTS, which was a similar predictive suite for trying to predict SEP fluxes in the near Earth environment. But anyway, we're using this as a standalone model, and that's part of the progress, the current progress in EPREM, its revival. So EPREM solves the focus transport equation on linked nodes that move with the frame of the solar wind plasma. What does all that mean? Well, some of the physical phenomenon that it captures are convection, cooling, adiabatic focusing, particle streaming, pitch angle scattering, particle injection, and the way that it does it, the grid that it uses, what I mean by linked nodes, are these streams of nodes, which I have here as circles. If it's hard to see, I'm looking at the green stream here with dots that are logically linked together in the code. So, so it's sort of, with nothing happening, it looks like this picture of a Parker spiral when you plot all these nodes at their positions. And that is different from what many people might think of as a simulation grid. Many people, certainly not all people, are used to a grid just being an arrangement of squares, or maybe an arrangement of tetrahedra or something if you're not glued to the Cartesian layout. But anyway, a fixed grid, right? And so that's an Eulerian description. These are different descriptions of fluids. They predate computer simulations, but here I'm going to talk about them in terms of grids, simulation grids. And so in an Eulerian grid, the things that we want to study exist at certain reference points. So we define this reference grid, maybe it's just these 2D square cells like this, and we express the flow properties as fields within each reference volume. Here the squares, or maybe it's a cube, or it's another shape. And then the fields that we want to know, say electric field, magnetic field, are functions of position and time. And the drawback or challenge to this is that accurately describing spatial gradients requires better and better resolution. So if you're trying to capture shocks, that is a challenge. There's a lot of numerical science and understanding behind that. But they're relatively easy to visualize. On the flip side is the Lagrangian point of view. And in this frame, the quantities that we are interested in exist on the marked particles. And so these would be the nodes in EPREM. And we describe the physical quantities that we want to know about at each of these nodes as a function of time. We apply the physical laws that we're modeling directly to each node. And what we get out of this is preclude the need to resolve these spatial gradients, with increased or adaptive resolution. But they're non-trivial to visualize, and so that's often the trade-off. So let me dig a little bit more into this focus transport equation that we're modeling on the Lagrangian grid, and maybe motivate why we do it in that way. So the focus transport equation describes acceleration and transport in the solar wind frame, in this specification of the focus transport equation, of a distribution of charged particles as a function of time, position, momentum, and pitch angle. And for those interested, this comes out of the Boltzmann equation. You can get this from basic kinetic theory, and make plenty of assumptions in some frame transformation. But if you turn the crank long enough, it'll come out. If you integrate over pitch angle, then you get maybe a more familiar equation to some people, which is the Parker transport equation in the inertial frame. But we model it with resolved pitch angle because we want to know the full distribution of particles. What we need in order to do this in order to get out to solve this for F sub S here, the particle distribution, is some specification for the magnetic field, the vector magnetic field, the vector velocity field, and the density, the scalar density. Because those things are scattered all throughout here in these derivative that are multiplied in different terms. So one way that people have historically solved that problem, getting the MHD quantities, is to couple it to another MHD equation. Take the output from an existing MHD equation. So Kamen Kodarev did this work in 2013. He coupled it to the Michigan Batts-Rust code. And they were able to model efficient SEP acceleration not only at an emerging shock front, but also at the compression regions surrounding the shock, and just to show how those compression regions are actually crucial to the observed flux farther out here in the simulation, but would be farther out in the heliosphere. Nathan and our collaborators at Predictive Science in San Diego have coupled EPREM to their MAS MHD simulation, and they've been doing this for over 10 years now, and this was an earlier work on it in which they not only showed how a fast CME, a simulated CME low in the corona produced a broad longitudinal spread of SEPs, but also that the effective dose at various points in the simulation volume to calculate from the flux could be over the acceptable limit for certain crude missions, which is a thing you want to look out for when you're out in space. And that work sort of evolved into Predix, which I mentioned earlier, which was an online tool for taking spacecraft data from certain spacecraft and propagating it out with EPREM to various points in the Earth, Moon, Mars system, preparing for, say, missions to Mars or the Moon. And Phil Quinn in 2017 did some of these validated this combination of simulations and data for for 5 SEP events in 2012. It showed the predictive power and the forecasting power. And then more recently, with our collaborators at Predictive Science, we have used a tool called STAT, which is still EPREM and their MHD model MAS, with some additional visualization tools. And we modeled the 2000 Bastille Day storm, and Bastille Day, if you want. And we showed, one of the things we showed that was that not only was the compressions around a CME as important as the shock in creating the flux of solar energetic particles at different points throughout the simulated heliosphere, but when we fit a broken power law to the fluence, which is in log space is a straight line to one point and then straight line beyond that with different slopes, and then plotted the indices, spectral indices of the slopes of those lines against each other, we found that the lower energy slope is very consistent, and that's in the orange box here. The lower energy slope is on the bottom axis here. Is pretty constant and is consistent with a process called diffusive shock acceleration. I'm not going to get into the physics of diffusive shock acceleration. It's a commonly attributed way, it's a weird sentence, of accelerating particles to these energy of shocks. But then the spread in the higher spectral index, meaning the slope of the higher energy part of the spectrum, is very wide. And remember, this is in log space, so a few numbers is a few orders of magnitude. And what we got out of this is that when we look at, say, ground level events, GLEs, from the solar cycle during which that event occurred, we see that they have a similar spread in the high energy SEPs. And so we realize that what we're seeing here is some indication that the intra-event variability, meaning the variability of the spectra at different points throughout the heliosphere in this one simulated event mirrors the inter-event variability of all of these other ground level events, these 23 other GLEs observed in the solar cycle. So that another way to say this is that the observed variability in all these different events could just be because of where you're viewing the accelerator, where you're viewing the source of the SEPs, rather than them being distinct physical processes driving the event. And this is, of course, relevant to widespread events as we explore the whole and get measurements throughout more and more. So those were all examples of EPREM coupled to sophisticated MHD simulations. Why use uncoupled EPREM, which I have told you already I'm going to do? Well, aside from the advantages that I just showed, there are some distinct disadvantages to coupling to other models. First is that all of these couplings have been unique to a specific model, say that's Russ or Maas, and they've all been hard-coded, meaning written right into the code. And if you've ever had to maintain software, that should make you squirm or sweat a little bit because it's really frustrating to see and hard to maintain, which I mentioned there. But beyond that, some of these implementations contained a lot of redundant code because, say, you copy paste one coupled model and then change the variable names for a different MHD simulation. And this all blows up and becomes very challenging to maintain as in the software sense. But it's also really inflexible to say something changing about that MHD model. Maybe they change from NetCDF to HDF5 output. And you've got to rewrite everything if you've written specifically for NetCDF. And then, of course, incorporating new models. You're not just going to copy paste every time and expect to be able to maintain it. So down the road is a more sophisticated model agnostic EPREM. But for now, using uncoupled EPREM is our best approach because doing so with its idealized cone-shop model, which I'll describe in a second, allows us to both quickly explore parameter space because it's very fast when it's not relying on outside MHD, some MHD, and to focus on the post-acceleration transport effects, to focus on what's happening after it gets accelerated. We're not using a very physically realistic CME in this. And so we're not focused on the physics of what the CME compression regions are doing. We're focused on what happens after and how it spreads. And so then all this is, of course, at the expense of missing more realistic particle acceleration. So quickly, what is this built-in shop model? It's essentially a cone of influence that doesn't, that it just exists inside the simulation at every time step, propagates radially outward, which is an important caveat if you understand anything about CMEs. But inside this cone, it solves the Rickin-Gounod equations for the magnetic field, the velocity field, and the density. And then outside, it just emulates or creates a Parker spiral. Okay, so very simplistic MHD. That's the outside, right? And in order to initialize the problem, and in order to have something to start with, when we're solving the focus transport equation throughout the heliosphere, we need a spectrum of particles. Here we specify it, and EPREM we specify it as a flux spectrum, which we then convert to the particle distribution. You can go either way. But the parameters of this, so it's essentially a power law, which is the E or E naught term here, times decaying exponential. And so what that does is it causes basically a downward flat or straight slope up to a certain cutoff energy, and then it rolls over. It's also called rollover energy sometimes. And we typically model protons. You can use other charge to mass ratios, but since EPREM has no interspecies coupling, it really doesn't make sense to do so at the moment. Maybe that's future work. But it's in there anyway. And then all the other parameters are, say, a reference energy, which is E naught, a reference radius, which we typically use for 1 AU, a radial decay rate, which is maybe 1 over r squared or 1 over r or something we sometimes play around with the radial decay of the spectrum from the inner boundary, just to see what kind of results we can get. And that's how that exists everywhere until the shock or something else passes through it. Another important physical quantity in EPREM, especially for this study, is the mean free path. And for a long time, we just specified the mean free path as a function of rigidity, which is defined down here in CGS units, because it makes a lot more sense to me in CGS. It's essentially a ratio of the momentum to the charge of the particle. And then a radial power law again. So for a long time, that's what we did in EPREM. Recently, we added the option to scale the mean free path by the inverse of the magnetic field, or some power of that, as an attempt to sort of mimic turbulence where it didn't necessarily exist, or to get a more realistic definition of the local mean free path when it comes to particle acceleration in little turbulent quantities. So I will, most of the work that I'm going to do is using this bottom one here, the inverse B scaling, but we did do some a run with the radial scaling just to see how much it changed things. Okay, so a little bit of motivation for widespread events, now that I described EPREM a bit. This is very similar to a picture I showed in the introduction. I referred to it as the canonical picture of sort of widespread observations. This was first published in 1988 by Kane et al. And so it is not actually 4 different satellites observing. It's a, what's the word? Can't think of it. It is brought many observations brought together to make these flux profiles, and they're all at, I think, 25 MeV, but they're different events. Now, as I said, some of our work has shown that maybe the variation in different events is just due to where you're observing, so there's still validity to this picture. But it's provide a very good description of the way that your perspective of the CME and the shock can lead to different flux profiles throughout the heliosphere. More recently, Don Reams sort of, I don't know about recreated, but improved this figure and expanded it a little bit and published that in 2023, showing, a more nuanced take on basically the same information with some additional observers at wider angles from the FLAIR location. But the picture remains the same. For an observer, say over here on the right of the screen, which is observing the CME coming off the west limb, they see a sharper rise in SEP fluxes, whereas on the opposite side, the observer who sees it coming off the east limb will see a slower rise, a peak farther along after the initial flare. And then down here in the center, there's more of a plateau, and then peaks off to the left and the right of that, and all of this depends not only on your observing geometry, but your connectivity, your magnetic connectivity to the flare source. So now that we are in the era of multiple spacecraft throughout the heliosphere, we're starting to observe this stuff essentially in real time. Well, without having to cobble together a bunch of different observations. And so, extremely well studied widespread SEP event occurred on the 29th of November, 2020. This is from this is a paper by Koloff et al. From 2021. On the left are electron and proton fluxes from a few different observers. Solar Orbiter is up top, Parker Solar Probe in purple, Stereo A in red, and then some L1 observers, ACE and SOHO in green down here. And in case you can't see it, the flare is moving off toward the PSP and stereo plots right here. That's where the arrow is pointing. And so in their analysis, they proposed 2 possible scenarios for this widespread SEP event. If the flare is over here, why did Solar Orbiter over here observe some fluxes, and why did the L1 observers also observe fluxes over on this side? One is that SEP acceleration along a broad CME front, meaning like the expanding CME driving shock, with causing mainly parallel particle propagation, right? So the wide CME front is accelerating SEPs along all of itself. The other possible scenario was that there's efficient cross-field or perpendicular particle transport with spreading occurring close to the sun, so early in the event, and then traveling along connected field lines to these observers.
Oh, yeah.
And they admit these are relatively extreme, and so there could be a mix of these two things that cause the event.
So may I interrupt you?
Yeah, please.
How would cross-field diffusion or cross-field transport be efficient?
In this scenario, so what they're proposing is that efficient cross-field transport places particles on, say, the
Hold on just a second.
Yeah.
You know, in terms of the SEP acceleration. So in order to focus more on my question,
okay,
why would be cross-field diffusion as efficient as the SEP acceleration of the CAD?
well, they have to be accelerated first. It's not purely cross-field diffusion. Is that so? So they are accelerated, but not necessarily all along the CME front.
Okay, that's a different picture then.
Yeah. So those are the two, and maybe I didn't.
Sorry to interrupt you here.
No, that's a fair question because maybe somebody else had it. Maybe I didn't elucidate this. These are two possible explanations. There are two possible explanations for why the event was widespread. So yeah, possibly there's acceleration all along the CME front, possibly there's acceleration in a few spots, and cross-field diffusion then led to the widespreadness.
So that's what you assume in your scenario.
That's what those authors assume, or what they propose, yeah, as a possible explanation.
Okay.
Yeah. I will actually, yeah, we do think we see that in our simulations, but that's.
So I'll just say that none of that was new, because I remember the same discussions in relationship to Ulysses.
Mm-hmm. Can you mean in terms of?
In terms of cross-field diffusion versus the spread of the acceleration region. I remember those arguments very well.
Yeah,
and also,
probably.
Of course, Ulysses had the unique situation that cross-field diffusion also meant going up or down.
Right. Yeah.
And so it was something that people really wanted to study in terms of Ulysses.
Yeah, it would be nice to have another Ulysses out there, or something out of the plane.
Yeah. Well,
Plane right now.
solar orbiter is going higher, but it's also close.
Yeah. The new thing here, sure, the physics certainly is not new. So it's not a surprise, or it's nice that we're not inventing physics. But the difference here is that there are multiple observers observing this event, not one observer observing multiple events.
Well, there were still multiple observers in the time of Ulysses. It was not as widespread. So.
Sure. Yeah. I agree. This is certainly not the only widespread event. Yeah. I'm showing a few widespread events from the modern spacecraft era, where we have because it's been a hot topic in the context of all of the observers that are out there. But yeah, I don't mean to present this as the first observation of widespread events. Okay, so let me move sort of quickly through these. There are some more examples. I don't want to, we're getting short on time. So Drake et al. Also published some research on the 17th of April 2021 widespread event. They attributed it to multiple injection sites along the shop front. Okay, certainly not the only one to be explained with that. And then a somewhat similar explanation for another fairly well-studied modern era widespread SEP event where they attributed it to good magnetic connection to the shock, but not necessarily always the strong shock. Sometimes to the weak shocks, so accelerating hydrogen SEPs. But let me continue on to make sure I get to my results and just mention to wrap this up what we mean by a widespread event. And essentially, the first point here is that you can put a number on it. I'm not interested in putting a number on it. Maybe someday it will be valuable to say that there's a threshold above which something is a widespread SEP event and below which it is not. I'm sure there will be a whole host of definitions in a few years. But anyway, the whole point here is that I don't want to get into what qualifies as a widespread event. We just wanted to model SEP events and see how we can change the longitudinal spread of them to try to understand what physical factors might be important in that. And so we take a sort of, when you see it, and I said we want to see if it enhances or suppresses it. So let me get on to the results. We're running EPREM modeling particles with energies from 50 keV to 500 MeV, and what I would call a fairly typical solar wind. We can argue about these parameters later if you want to, but they're not totally wild, which is fine for us. And then our background spectrum has a fairly soft power law at lower energies, and then rolls over at 1 MeV. So it's a fairly soft spectrum, and that's all I'm going to say about that. And then the shock has an opening angle of 9 degrees, so it's pretty broad, and it's a strong shock, hydrodynamically strong in terms of, it has a compression ratio of 4. It decays exponentially behind the shock front. The quantities decay back to their unshocked values. And here's where you throw the tomatoes at me. The shock propagates outward radially at 1,200 kilometers per second the whole time. That's not physical the whole way. This is a drawback of EPREM, uncoupled EPREM, and I'll get to that later. But this is what we're modeling.
And I guess it has no structure.
Yeah, right. It is. That's right.
Just great.
Yeah. Except that it's
even less than a physical.
Yeah, right. I think that's right, because it's decaying behind shock. It's not driving out. Yeah. Okay. So then we fixed all those parameters, and then we varied a number of them. I'm not going to show all of the variations, but some of the important ones, in my opinion, in our conclusions, focus on whether there is or is not perpendicular diffusion, varying components of the mean free path specification, which also affects diffusion, and then the strength of the shock, the strength of the shock front as it propagates out. It actually really the strength of the gradient in the shock points. Okay. So this is a picture of what the shock looks like at different radii for 2 different variations of the shock profile, and you can see it's very simple. It is a flat shock front moving out. This is at half an AU, and this is the bottom line is at 1 AU, so it gets 1 AU later, of course. And then in we change the shock profile, it softens this leading edge here a little bit, and then decays. Both cases decays exponentially back to unshocked values behind. Okay, and so we scattered some observers at different locations throughout the heliosphere. One group at half an AU, one at 1 AU, and observers are cheap in EPREM. Point observers, I mean, they're on a fixed grid. they're interpolating the node, the Lagrangian nodes around them, which is, can pose its own problems, but we stuck some right at the center of where the shock originates, where the flare is. We stuck some on either side of the expanding cone. We stuck some at plus and minus 90 degrees, and then some way out 180 degrees away from the foot location, as far away as you can get, to try to understand the longitudinal spread. So from our baseline simulation run, we get fairly not especially surprising flux profiles at different points in the heliosphere. I'm showing here, and this type of figure will be the same every time. Top row is 1 MeV protons, followed by 10, and then 100 on the bottom, and then time marches from left to right, 2 days, 3 days, 4 days, 5 days. And as the shock moves out, 1 MeV protons fill these streamlines here. This is likely due to cross-field diffusion over here, and we can get some flux out to 100 MeV that diffuses back to the observers way back here at 180. And those time profiles of those fluxes at each observer look like this, where we're seeing right at the flare location a quick rise in SEPs right before the shock arrives, this dashed line, and then decay behind. Now, we've already discussed how the downstream structure of the shock is essentially, it's definitely unphysical, but it's essentially not there. So this is not as much of a part of we're not as interested in the physics of this in the downstream region as we are in what's happening before. But we do see spread all the way back to the observers on the other side of the simulated sun, and east-west asymmetries in the two observers at right angles to where the flare is, and then even some asymmetry outside or near the shock cone. But when we turn off the perpendicular diffusion, that makes a big difference in the fluxes that certainly that make it out to the other side of the sun. But in addition, those that make it to the east and west observers on the flanks as the shock is moving by these observers over here. So to go back to baseline, there's much less flux at, say, this observer at day 3, and that is this flux here. The baseline run is almost certainly due to perpendicular to cross-field diffusion, since it's gone when we turn it off. We started to wonder, well, okay, why is there flux here? How do we turn that off? What's likely causing that? And so when we just turned off diffusion, including parallel diffusion, not surprisingly, you don't get a ton. You get some acceleration of 1 MeV of low energy particles at the shock front, and they're the spectrum's higher near the sun because they fall off radially. But other than what gets pushed out by the shock, there really isn't much. So that points to diffusion as a big component in adding flux in spreading it out to these farther observers over here. So when we change the mean components of the mean free path, sorry, okay, I thought I had a question. We see this in different ways, where the mean free path not only affects diffusion, but when we change the reference, which is really just the scale value of the mean free path, the constant scale value, there is a lot more flux of lower energy particles even by day 3, 4 out at these out behind the sun and outreaching these observers on the other side of the sun from the shock, and that is all likely due to diffusion. But the other aspect of cross-field diffusion, but the other aspect of this is that there's nothing at higher energies, and that is we think due to the fact that there is just not enough time for these particles to gain that much energy before they leave the acceleration region. Even though there's a simplistic shock, that mean free path that is narrowed in a physical compression region, say on the wing of a CME, on the flank of a CME, which again is not in this model explicitly, but that sort of reduction in mean free path allows particles to accelerate before they escape. Here, the mean free path is larger by a constant factor, so they're able to spread more, but they don't attain high energies before they do that. Okay. Yeah, go ahead. I really got to move along, but I do want to hear. Yeah.
So I'm missing sort of a very important component here is the self-consistency of all the processes involved in determining the cross-field diffusion, whatever.
Okay.
So I'm just seeing what you do. You assume a sort of a cross-field diffusion, how widespread that's going to be. But this also entails that you more or less ignore the processes leading to that cross-field diffusion.
Okay. That I'm not exactly sure what you mean by ignoring the processes that lead to it.
So the cross-field diffusion, before particles do cross-field diffusion, it needs a little bit of energy.
Yeah.
To get there.
Sure.
Because it's, and then usually the particles don't like to go across feedback. And if you give them enough turbulence, then maybe. But I just don't see all these parameters playing together here.
Okay.
So what you're suggesting is he needs wave-particle interactions.
Right. Yeah.
At least, let's say, that goes up to, as he says, to higher energy. That's the very crucial point. How get you up to higher energies, which is also not explained in this picture here. You just say, well, yeah, there is cross-field diffusion, right? It is maybe. But what is the efficiency of that cross-field diffusion at higher energy? So all these processes, I'm sort of missing the self-consistency of all these processes playing together.
Yeah, I mean, there is no, this is a test particle sort of setup, right? I mean, there is no feedback from the particles to the fields or to the plasma.
So that's the way you see it as a test particle approach.
Yeah. Yeah.
Okay, all right. Then,
But you
That's
can still gain insights from something like this.
yeah, but how
But
limited is that?
yeah, that's true, but it can still
I'm not
point
saying,
you in the right direction for more detailed modeling.
Sure. Yeah. Yeah. But I mean, I don't know the self-consistent yeah. I mean, I would love to know who's doing self-consistent plasma modeling up to hundreds of MeV. Like that would be very valuable throughout the heliosphere.
well, you don't have to do it up to 100 kV or
MeV.
even higher. I'm just saying that when the processes start to evolve, there is a section where it is you can model it, and then of course the mean free path is getting too bigger and all that kind. I'm aware of all that, but I just don't see the approach at all here.
Yeah, we can always let Matt finish too and then talk offline.
True. Yeah. We definitely, yeah. So let me run through. So the shock, lessening the shock profile was also a major contributor to reduced flux, reduced spread in flux, meaning, so essentially meaning a weaker shock. But conductivity, for the observers that were somewhat connected to the shock, they still saw observable fluxes of even up to 10 MeV protons. So I think that's consistent with some of the existing observations. Some preliminary results that I'll skip over, but we are working on a paper comparing specifically the 29 November event to some spacecraft and seeing some initial promise in our comparisons in terms of event rise time and decay. Okay, let me summary and we'll talk more about this. So two things: significantly reduced wide longitudinal spread in SEP fluxes. suppressing the perpendicular diffusion and the weaker shock gradient. Increasing the reference mean free path significantly increased the longitudinal spread in SEP fluxes. But as I said, the particles didn't gain as much, and there weren't as many high energy, meaning 100 or so MeV, 100 to 500 MeV particles that were getting into those locations. And then the changes to the mean free path, the inverse magnetic field scaling, and to the rigidity dependence of the mean free path, which I haven't shown in this, which is in the paper, had little effect on the farthest observer, but they did strongly affect the timing of peak fluxes and the evolution of flux as a function of energy at all the other observers. Oops. I lost my caveats. So yeah, there are a number of caveats, and maybe I'll leave it on this. Sorry, the next one, so that people can explore this more if you want to. Didn't have time to. A QR code for Zenodo link, but anyway, that Zenodo link is to a record with this presentation, and I'll update actually some forgotten caveat slides, and I'll make sure that this most up-to-date version is up there in the record, and also some references to papers that I talked about. EPREM and the analysis libraries that I've written are on GitLab, all under the Open EPREM group, and the project, whatever it's called, and then that's my email if anybody wants to get in touch. Okay, so yeah, let's close the presentation there, and then we talk after other questions. Some caveats that are worth mentioning, which are related to what we've already gotten to, or what we've already heard come up, are that yeah, this is a very unrealistic shock. The downstream region is essentially empty. There's no turbulence. The flux tubes are no turbulence anywhere in the MHD. We can parameterize it, but that's the most that we will do until we're able to implement model agnostic coupling. And this is something that we're chasing funding for, haven't gotten, but keep making slow progress toward. And what that means is just specifying standards for what sort of data types this could take, different file types from an MHD simulation, and feeding it in without EPREM knowing anything about the MHD simulation, just knowing how to get the fields out of it. And that will open up a lot of different ways to incorporate more realistic MHD processes into the solving the focus transport equation. And I think that's really it. Yeah, I mean, I think all the other caveats we sort of come up. So yeah, I mean, in terms of self-consistency, I worked on hybrid plasma simulations with you, and we did the shock modeling, and none of we didn't accelerate particles. We were trying to get the superthermal population out of thermal population. We certainly weren't going to get particles up to 100 MeV or 500 MeV, and those are the particles that we're trying to predict. So that's the thing that I would love to learn about people, how to model up to those energies with a self-consistent plasma simulation, because I think that'd be so cool.
Actually, speaking of self-consistency, so just thinking back to the EPREM model again with the Lagrangian frame, or the Lagrangian, since I'm new to EPREM. So the nodes, again, you said, so they're kind of moving around, and the fields are just like, say, a Parker spiral imposed field that it's getting, or is that when you have a complex MHD to get the field?
Yeah, so for this, internally, when we're running uncoupled EPREM, it actually it goes through every node and it says, where are you? Okay, here, according to Parker spiral, with this particular, this magnitude of magnetic field at one of you and this solar wind speed, this is what your magnetic field, and yeah, this is what your magnetic field is. This is your solar wind speed, or your different components of your velocity, and then the density is falling off as one of R squared, so here's your density, right? And so it's like taking these Eulerian quantities that are never actually on a grid anywhere, and applying them to each node. When we couple in MHD, it interpolates, basically. It goes through every node and says, where are you? Okay, because every node knows it's r theta phi, could be any coordinate system, but it's r theta phi coordinates. And it says, okay, I have MHD at these 8 points. And so you interpolate the value from that, from this grid of the other MHD simulation. And then that's your value of these various MHD quantities. And then when we're doing the shock, it's similar, except that it just says, where are you? Are you in the shock cone or not? And if you're in the shock cone, then it updates the magnetic field density and velocity based on the Rankine-Hugoniot, MHD, magnetized Rankine-Hugoniot equations.
Yeah, thanks.
Okay. So I saw your thought. Do you want? Is it a question yet?
Yes.
Okay.
So basically, you assume a spectrum going in. You're not having acceleration at the shock. You choose those parameters you use to create the spectrum.
There's initial spectrum through which the shock propagates.
Of course.
Yeah, and then the change in B, V, and N cause the spectrum. Yeah.
Sure. So this is purely propagation of the shock where you've chosen the parameters. I just want to confirm that.
Yeah. Good question.
That I understood.
Yes. Thank you.
Yeah, I think where we have the tools on, with the cross diffusion on that plot, and we have this virtual observation points, so that figure, and that keeps going back to the observation figure from that more recent paper.
Mm-hmm.
And when I look at various locations, they show where the signature increase happened. Have you looked into any timings of it, and if there's any pattern to just for where they're located, where they start seeing this jump
See
in
if
locations?
Okay, so let's take my baseline simulation run and like this, these observations, or I'm not sure which.
I think so.
Yeah, because I was referring to these as like the canonical pictures. Yeah.
Yeah, the ones that actually had a multiple stage observation. Yeah, something like this.
Yeah. Yes, we do see similarity. There actually is more in the ones that I go really quickly over in our forthcoming paper, where Parker Solar probe sees a sort of plateau like this, and EPREM produces a similar plateau. One thing that I will say, let's see if the what is the one thing I will say that is another caveat that I forgot that is relevant here in terms of timing, and this is the reviewer pointed this out, and I really appreciate it. This is where a good reviewer is good. The fact that our shock propagates outward at a constant speed is probably is maybe even worse than the lack of turbulence and other caveats in this, because it really changes the arrival time and the profile, the flux profile before the shock arrives. So typically, shock launches out and it's really fast, but then it decelerates rapidly and then it propagates out at a constant speed. And I tried to implement that really quickly in response to the reviewer, but I'm not able to do it in a clean, well-documented way. And I don't want to publish a change before. Anyway, all this is to say that's a huge caveat that I think is really important in comparing this, where say the flux rises, or I mean even this one, but the flux rises and plateaus and then the shock arrives, to say like this, where at a similar relative position, the flux rises really quickly. Now our time scales may be a little bit different, but yeah, I acknowledge that as a big drawback to this.
I mean, you said the reviewer is saying the more realistic cases, it accelerates first and then plateaus. It's just modeling a plateau timing of it, I guess. You need to.
Yeah. so that's what right now it just doesn't exist. Right now the shock propagates outward at a constant speed, and so that's missing.
So based on your previous slides, it looked like these were results for just H+, right?
Yeah.
So do you think your findings would also hold true for like helium that you're
Yeah, well, we don't have, EPREM doesn't have any interspecies interactions or anything. So it's really just a constant charge to mass ratio. It's like just a multiplicative factor where okay, we haven't really explored it. I've made some plots of multiple species, but they tend to just be similar fluxes that, you know, when you plot flux per MeV, you know, counts per MeV per nuke. So like, you know, normalizing the energy to the atomic number, they basically are just on top of each other, or not on top of each other, but like stacked, I guess is what you'd say. I don't know, where can they see me? I'm moving my hands. I don't know, the people online.
Follows you, yeah.
Okay.
I think
So yeah, it's definitely not mature enough for us to draw any results. Yeah.
So I assume that you have time-dependent theta VN in your simulation, because the way you showed Hillary Kane's results, that would more or less indicate that there is a theta VN change in the change of the work speed of the plasma.
Mhm. Right. Yeah, this, as I said, this shock.
Or is it not in your simulation? I mean, I accept it if you say.
Yeah, it's not, the shock just propagates radially outward.
Radially with a constant speed.
Yeah.
Yeah, all right.
Yeah, so those are the two things that
Maybe.
I'm working on tomorrow.
Okay.
Is deceleration and motion, you know, changing theta again. But I mean, to be totally honest, and I'm talking to the software developers, the research science engineers, software engineers in the room. This is since we are moving toward an MHD or a coupling, a model agnostic coupled EPREM. I have to think very carefully about how much time I want to put into this internal MHD specification if I'm just going to rip it out in 6 months. Because that, I mean, a 2-day project can take me a couple of months if I'm not careful. And it would be better, in my opinion, in the long term, to not let EPREM ever calculate another MHD quantity and just feed it in. Even if I feed it in a simple cone shock, I have more control over that shock, and if I just make it externally and feed it in, than if I try to put it in the cone. So there's my little soapbox. Okay, I've kept you all for a
So
long
this
time.
is, I'm trying to understand the dimensionality of your model.
Okay.
So it's essentially, are you treating this essentially two-dimensionally, or?
That in this, no, I think no. I feel comfortable saying no. So it is a 3D model. I've put all of the observers in the ecliptic plane for this.
Sure.
The set of runs. For the other ones that I showed, where we're due November 29th, 2020, they are not all in the ecliptic plane.
So does the CME then have a latitudinal extent?
It does. It can differ from the longitudinal extent. In general, it does not in these. So in these, it has a 90-degree opening angle in latitude and in longitude.
That's a weird CME.
Yeah. Okay. Fair. I mean, and
for the model though, so if you can get something that you understand well, then you can kind of just tweak.
Sure. Yeah.
I didn't mean that as a criticism.
No, that's fine.
It is. Understand what you're doing.
Yeah, it's a great question. It's a fair question. It's one that I thought of long enough ago that I implemented the ability to have different widths in latitude and longitude, but also long enough ago that I didn't think about that when I started running these, and I ran them all with a circular cone instead of an elliptical cone. I think that would be interesting to look at, actually. To just do one more run, they take a couple hours. So yeah, maybe I'll squish it a little bit in latitude, see what we get. Because they do, the point observers interpolate from nearby streams in 3 dimensions. So that should affect what they see when they're interpolating from streams above and below.
Great, well, for the sake of time, let's thank our speaker again.